And now we're going to start going after the main engineering thing of interest for flows in other turbulent situations, and we're going to do that by looking at drag. So the drag is going to be the force that prevents continued motion of the object, or that the fluid exerts on the object, depending on which way you view it, for an object in a moving fluid. So we're going to look at external flows here. So we're going to define external flows. External flow is fluid that goes around or over an object. So this would be a cylinder with fluid going around it, a plate with fluid going over it, a step with fluid going over it, or step going down the other way. Any of those flows would be considered external flows. An internal flow is flow that occurs in a channel, a duct, or a pipe. That is, it's flow that is actually confined. So we're going to be looking at external flows now. For the internal flows, we already had the Moody diagram to get us the drag and the resistance to flow. But for external flows, we are going to have to use something else. So now we're going to define some terms. We're going to define the drag coefficient. So the drag coefficient is going to be the main parameter that tells us the drag. So we're going to go after that drag coefficient in various ways. And here's its definition. Oops, that's wrong. So here's its wrong definition. Wrong. Run half rho v squared a. I'll write it again, but equals f d over 1/2 rho v squared a. So that's my drag coefficient. Ignore that thing. My drag coefficient is this. That's just a definition. This is your drag force. So this is usually the engineering thing of interest, one way or another. That's either the force you have to supply to keep the object moving through a fluid, or it's the force that the fluid is exerting on the object. It depends on an inverse way on the inertial effects, 1/2 rho v squared here, and of course it depends on this A, which is generally the cross-sectional area, but this is going to be defined differently for different objects. So will be defined based on the object. And we'll see there are a couple of different ways that that can be defined. So you have to be a little bit careful to make sure you're using the correct A there. There's also a skin friction coefficient. So that's the other parameter. Skin friction coefficient. Skin friction coefficient is defined, its label is C sub F. It's the shear stress divided by, again, that dynamic pressure, or those inertial effects. So that's what that is. So it's wall shear stress divided by inertia. So that's a skin friction coefficient. That's the local wall shear stress. So we've seen this before, right? So you can have local wall shear stress, but that shear stress may be changing as a function of position. So the other parameter that's often more useful from an engineering perspective is the average skin friction coefficient, which consists then of the average wall shear stress, which allows you to actually calculate a force. Because if you have this skin friction coefficient, you have to get a force on an object, you have to integrate that. If this TW is not average, if it's changing over space, you have to integrate over the entire space. On the other hand, if you've got an average skin friction coefficient, then you can just solve for the average wall shear stress and multiply that by an area to get your total force. All right, so those are the parameters that we're going to be going after. We're going to want skin friction coefficients and or drags in order to get our engineering results of forces needed to make things happen. All right, so this is kind of equivalent to the friction factor. So this is the external equivalent, external flow equivalent of that F, which was our friction factor, right? So we had friction factor for pipe flow, and we used the Moody diagram to get that. Now we're going to try to get C sub F and C sub D with various relations. All right, so let's just start with a simple one. All of these are going to be empirical. So once you're in this land, the way people get these answers is they do experiments and they measure forces. And then they try to come up with correlations that you can use to predict those forces based on various factors. So there are lots and lots and lots of these correlations. I tried to pick ones that seemed, relatively easy to use and that people generally accepted as being reasonably accurate. They are all approximate. This is all done by experimental work, so none of them is, truly exact. And you could find different people saying, "Hey, this other one's better. This other one's better." But nonetheless, you'll get the idea that these are good predictive tools, and you can try other ones if you're in a situation where the one you're using doesn't seem to be doing giving you the kind of accurate predictions that you need for your particular problem. So let's take a look at flow over a plate again. So we're now just looking at that same classic flow. Here's your plate, and your flow is going over the top, and we know that we're going to have some laminar region, then it might go turbulent. So, and we're going to look for the skin friction factor. If our transition is a lot less than L, that is, if there's very little laminar and mostly it's turbulent, then we can calculate the skin friction factor. The local skin friction factor is 0.455 divided by ln of 0.06 times the Reynolds number based on X squared. So that's your local skin friction coefficient. So not your average one. That's your one that's for your specific skin friction coefficient as a function of X. If you want the average skin friction coefficient, that's equal to 0.523 divided by ln of 0.06 Reynolds number based on L squared. All right, so that's your average. So you have access to both. These are for both for flow over a plate. This is good for Reynolds number greater than 10 to the 7th and Reynolds number less than 10 to the 9th. So that's the region for which this is good. Greater than 10 to the 7th means it is turbulent, very turbulent, and it's turbulent. It's pretty high Reynolds number because you have to have a small laminar region or this doesn't work. So this is only good for a very small laminar entrance region. The transition is very close to the front of your plate relative to the length of your plate. So that's what that's saying. And then this is just, at some point this relationship breaks down. You got to go find a different one. If your Reynolds number gets too high, you got to go find a different relationship. All right. So that's one set of relationships. If your transition Reynolds number is approximately the same size as your length, and that translates into a Reynolds number of less than 10 to the 7th. Now this is still for turbulence, so it's got to be greater than 5.5 times 10 to the 5th, but less than 10 to the 7th. Then your average skin friction coefficient can be written as this: 0.073 Reynolds number based on L to the negative 1/5 minus 1700 Reynolds number based on L to the minus 1. So there's another relationship. This is for this condition, Reynolds number less than 10 to the minus 7, but still turbulent. So we've got, two different average ones here. One for larger Reynolds number where you have more turbulence and basically no laminar region. One if you have a laminar region as well as a turbulent region, and you're trying to calculate the skin friction coefficient for that situation. So that pretty much covers your regions. Both of these are for smooth walls. So you have to be careful with this as well. The smooth walls for both of these, it turns out, of course, that surface roughness can have a significant effect. And in that case, you've got to go to other relationships. It can increase C sub F significantly. So you've got to be aware that if you do have a rough wall of any kind, these CFs will underestimate it. And of course, you can find other relationships that account for that surface roughness. And there's something similar to a Moody diagram that you can get for these CFs. We're not going to spend a lot of time dealing with that. I want you to be aware that surface roughness can affect your skin friction coefficient in turbulent plate flow. That's an important thing. Just as in pipe flow, it can matter, But I do not expect you to learn, the many, many, many relationships for all these different conditions at this time. If you go into this field, if you go into aerospace engineering or something, you're going to have to learn it all. But at this point, just know that it exists. So these are good relationships for smooth walls. If you know that surface roughness can matter, if you need to use that, you need to go find either a chart that accounts for that or find some different relationships that let you account for that.